and welcome to another episode of FooBar. In today's episode, we are going to talk about optimizing cost and performance in your Lambda applications. So if you want to know more about serverless, cloud computing, or software engineer practices in general, subscribe to my channel in the red button below. I post a video every Tuesday. So let's get started. Today is another cool interview with Alex Casalboni. He will be talking about optimizing Lambda for performance or cost, or we can see that both can get improved. So this is a really cool intro for the series. This is not a podcast. So if you have not watched the previous episode, we have Darko, and next week we have FooBar. So this is getting interesting. Let's get into the interview. So here with me today, I have an amazing guest. I have Alex Casalboni. He's a developer advocate from AWS. And I'm super happy to have you here. I hope you enjoy this interview as much as I did interviewing him. So welcome very much, Alex, to my FooBar channel. How are you doing today?
Hi, Marcia. I'm doing great. Thank you for hosting me. I think we'll have a great talk today about Lambda performance optimization.
Yes, I have not said the topic of today, so we are going to talk about...
I spoiled it.
You spoiled it, damn you. But yes, we are going to talk about cost and performance optimizations for serverless applications, but I'm pretty sure I put it in the title and in the thumbnail of this thing, so it will be there. It's not a secret. But yeah, that's what we are going to talk today. And I think you're an expert on that. You have been talking a lot about that topic. But first, I think it would be nice if you introduce yourself a little bit and you tell us what you do, where you are, and I don't know.
Absolutely. I'm a technical evangelist or developer advocate, up to you. But my background is in web development. So I've been working as a web developer since 2014, more or less. And I work in a startup. And then I joined AWS about 2 years ago because I love building applications. I love sharing and traveling and talking about these things.
Nice. And you're also a musician in your part-time when you have free time?
I am. Now I have a lot of free time, and I play the saxophone and the piano as well. Nice. And I'm Italian, so I'll be moving my hands a lot too.
Go for it. It's a video, so you can do it.
Yes.
Cool.
Awesome.
So let's go then to the topic of the day, that is cost and performance optimization. And my first question is why we want to optimize something, what we are optimizing at the end of the day.
Good question. I think there are two main goals there. Some developers and some organizations want to optimize for cost, meaning they want their solution to be as cost effective as possible, and that's a very reasonable goal. The other end of the spectrum is optimizing for performance, meaning that your workloads are very latency sensitive or customer facing, so you want the best user experience possible. You want to minimize the latency and, cut as many milliseconds as possible from your API response.
There are two use cases that are quite, I have heard a lot of stories about we want to use serverless because it's cheaper, or we have problems with serverless because latency and things like that. So I think that this talk can help a lot of people to solve those problems that they mention a lot of times, like, if you run your EC2 24/7, it's cheaper than to have your Lambda function running 24/7. But maybe that's not the case.
Well, if you look at the total cost of ownership,
exactly.
you can really, it's kind of hard to write down all the numbers that you should consider. I think today we'll mostly focus on the function per function optimizations, so that if we have 50 functions in your architecture, you may want to optimize the ones that are most used or the ones that are the most relevant feature in your application. So you want those to be more optimized than the others. You can choose and be very granular.
Yeah, and I think that's the cool thing of Lambda functions, that it's so granular that you can scale and improve the 20% of the code that gets 80% of the traffic and goes into the most of the costs. So
absolutely.
And when we were preparing for this, you mentioned that cost and performance are very related, and I would like to hear more about that, because in my head it always, if you improve performance, then cost goes to hell, and the other way around, and you know.
That's true. In the traditional world, if you want something to go faster, you need to put more money on the table. Usually, it's, maybe it will cost you the same and you can do some architectural or some code refactoring. But in theory, right, we come from a world where, you want to go faster, you spend more. And with serverless, sometimes it's true, but sometimes it's not true. Many times, especially we will see for some specific workload types, you might actually get faster and cheaper at the same time. And this is something I'm really excited about.
That's super interesting, and I think now I want you to tell me more about that. I imagine in the follow of this interview we will have more examples of faster and cheaper. That's kind of the unicorn land.
Agreed.
Yes, and what are like the main challenges that companies face or different customers face when they are trying to improve the optimization of their applications? Like what kind of things they face?
I think there are two main challenges. One is that usually optimizing means changing. And so you have friction because maybe you're not using a microservices approach. Maybe you want to re-architect the overall application. So you need to change a service, or, I don't know, go in parallel instead of in series, or, remove some parts of your code to replace it with a managed service, or, things like that take time, takes some experience as well. And so it's an investment. So the other challenge, I think, is trying to be data-driven. It's kind of hard, especially if it's a new workload, how much can we optimize? Is it worth it? Do we have enough data to prove that it's worth investing 2 weeks of our time on this? So I think today we'll try to answer some of those questions too.
Yeah, and I think I have heard so many people saying we need our application to go faster, but they don't know what is the current performance of their application, or even the whole cost of their application, because it's distributed into multiple cost centers and things like that. So it's very hard to measure or to try to improve something that you cannot measure or you don't have any measure for. So that's so true. And I think it's the same with how much you want the uptime of your application. Like some people say, we need to have 100% uptime. Is that realistic? I don't know. Even services like S3 have some times that they have hiccups during the year. So it's like even the most reliable services have so what is the right spot? But for that, you need to measure and you need to have the numbers.
It's always a trade-off of some sort. And now you can go multi-region. Now you can do a lot of the things that 10 years ago were much harder to do. But still, it's a trade-off. You shouldn't do it by default just because it's cool. It must be worth it.
Exactly. And everything adds work and everything adds costs and delays on going to market and things like that. So that's something. Sometimes people have so many tools in their hands and they want to use them all just because it's cool or because it's trendy or because they have them available. And I think it's quite normal for engineers to over-engineer everything.
Exactly.
Yeah, I imagine with cost and performance is the idea of this evolutionary architecture is very important, where you can build very modular parts of your application that you can improve with time according how the system behaves. If you have a lot of work done in one particular service is very used, a lot of people are using, everybody's hitting, then you can spend time improving it.
And I also talk to many developers and engineers who are like, I don't care about cost, I design the best architecture. Well, the idea that you get closer to your code, closer to the deployments, closer to the customer also means that you have to own a part of the cost optimization and cost estimation process sometimes. So designing something that is cost effective and that can be improved over time. is a plus.
And now that you mentioned the cost and you put it like that, I'm thinking about so many developers don't have visibility on how much their applications are costing and how much it costs to run. And I think with serverless technologies, having that closer to the developer and also teaching developers about cloud economy and how they can make best decisions they can is something super important. What is your...
Agreed.
Yeah. Because how you can optimize again if you don't know what you're optimizing.
Well, most developers optimize for performance, and the fact that these two dimensions are aligned sometimes is a great plus in serverless too. Now you can optimize for one and likely the other will follow, but not all the time. So I think it's worth knowing when these two dimensions align and when they do not. And we will look at some charts and diagrams and patterns in this talk.
Nice. One thing before we move to the main topic is you mentioned some best practices on overcoming these challenges that maybe you can mention now before we move on.
Sure. So I usually talk about two macro categories of best practices because a lot of developers still think that, well, it's true that cold starts are quite a big pain in serverless, and that might be true for some workloads. So I tend to divide my optimization best practices in two categories. The first is those best practices that allow you to minimize the cold start effect. And the second category is all those best practices that allow you to optimize all the other executions, which, by the way, are usually the largest majority of your execution. So in my opinion, that's where you should focus the most.
Yeah.
So just to give you a few,
exactly.
If you talk about cold starts, usually you want to minimize the size of your deployment package. You want to optimize dependencies. You want to sometimes even get rid of dependencies. So you can do a lot more with the core of your language. So you really shrink and minimize. You may want to uglify if you're using JavaScript, or compress if you're using other languages, to really shrink. Every kilobyte you can shrink is worth shrinking. And usually for cold starts, unless you go for something more sophisticated like provision concurrency, for example, usually that's all you can do.
Yeah.
There are a few other tricks, like trying to, for example, if you have multiple functions in your files, you might have one JavaScript file with 5 functions there. A lot of developers like to do that. So oftentimes you end up with a lot of initialization code at the top of your file, and maybe there you have objects used by only some of the functions in that file. So by doing that, you're basically maximizing the cold starts of all these functions. So what you can do is you can lazily initialize these objects only inside the functions that need them. So we call that lazy initialization. And this is sometimes confusing because, well, if you have one function per file, it doesn't matter at all. But, these are micro tips that are worth knowing.
But I think with the multiple functions per file, sometimes people think that it's better because your Lambda will be warm because everybody is calling it and it's called all the time. But then on the other hand, you have more dependencies, you have bigger package to deploy, you have maybe some initializations, and then at the end of the day, it's expensive to have one monolith function than to have a lot of smaller functions that just load faster and do the...
Well, you might even have very small functions all in the same file, but it doesn't mean that they will all be warm.
Exactly.
Each and every one of them will have their own cold start. And if we have too much initialization code shared across functions, well, you're not doing a great job there. But hey, different languages have different challenges.
Exactly.
And just to give you an example, when I first started using Lambda in 2016, I think, I was doing Python machine learning libraries inside Lambda, and my library took 2.5 seconds to be imported.
Wow.
And, even before being used. So in those cases, you want to isolate those functions or do some sort of lazy initialization for sure.
Exactly. Like the problems are very different in the serverless world and in the normal application world when you just load the application once and then it's running and warm and there. Yeah. So maybe now we can go a little bit to a tool that you created that was the reason of all this interview. I was very interested when I saw this tool that you created for improving the performance and the optimization of serverless applications. You talk about this tool in reinvent as well, and you've been, working on this since forever. So I would like to know a little bit the story of the tool, how you created, how we got here, and
Sure, it's called AWS Lambda Power Tuning. I don't even remember where the name came from. It was a very long night of 2017, I think. And what I was doing at the time was I had a few functions in my company back then, in the startup. And I wanted to optimize them because they were these very, long cold start Python machine learning functions, and we wanted to optimize them because latency was critical. So I was doing all of that manually, right? So what you do, you open the function, you change the memory configuration, and then you click test and you see the number. But then, it's not very statistically relevant. It's a lot of manual work, and maybe you want to do it every time the code changes. So, you can keep the optimal value updated.
Yeah.
So
maybe
basically
you can
what
explain a little bit, because I think now we are getting into the details on how Lambda works. And I think maybe you can spend some minutes explaining a little bit about what kind of optimizations you can do in Lambda, because we are getting to small details that are relevant.
The idea I had back then was that, hey, the one thing I can do, so in my list of best practices, there is one that doesn't force you to re-architect everything. You can do code refactoring, architectural refactoring, you can change everything, but there is one thing that you just do it and you don't have to change anything else, and that is tuning the memory configuration of your functions. Now, to do that, you don't need to change anything in your code. You don't need to change the rest of the architecture. But it's one thing you can do, and potentially, and that was the idea back then, you can automate this. You can make it, you can build a tool that will do this for you and extract all the data and show you which is the best memory configuration.
And I think one important thing to mention there, that is when you tune the memory of a Lambda function, you're also tuning the CPU of the Lambda function.
That's the most important part, and I didn't get it back in 2016 when I started. It took me a while to understand it. That's why I called it power tuning, not memory tuning, because if you give it more memory, you also are giving your functions more CPU, more networking, more everything. So I just called it power now. If you listen to me, if you hear me talking about power in the context of serverless, I'm talking about the memory configuration. And that's a great idea, because especially, and we will see it, especially in particular workload types like CPU-bound workloads, if you give it more power, you will have a lot of more CPU power. You might even have more cores available. So if you're doing things like multi-threading or stuff like that, you can actually go much faster.
Exactly, and I think that's something that it was quite mind-blowing for me as well when I discovered that I never understood what I want to give more memory to my function that is just doing very small thing. It doesn't need much memory, but the moment you start playing with this, and I was doing it manually because I didn't have your tool available. I didn't know about that tool available when I was playing with this many years ago. It's just like, it's so annoying that you go and change the memory from 128 megabytes, that is the smallest one, and you think, I'm building a super simple Lambda function, it doesn't need more than that, and then you change it to something very big like 1 giga or something like that, and then it's like goes super fast and it does everything, and you're like, oh, interesting.
Yeah, but then the trade-off is, am I paying more or not? Because more memory also means that the cost per execution for 100 milliseconds is higher. Exactly. And that's kind of proportional, right?
Exactly.
So if you want 10 times more memory, you can expect, if the execution time is the same, to spend 10 times more. Sometimes you don't want that.
And also, sometimes you want to stay in the sweet spot of 110, 120, because if you go under 100, you're paying for a kind of, at least that was my thinking when I was designing these things many years ago. If you go to 70 or 80 just by improving the CPU, does it really make sense? Unless you want to go faster, but from the cost perspective. So it's a very interesting balance to play with these numbers. And I'm super excited to see the tool that will save me a lot of nights of my previous life.
Yeah, so I was there that night literally doing it manually, and I started building something super scrappy, super simple to automate this. And then I thought, but hey, maybe I want a way to visualize this. Maybe I want a way for people to deploy the same thing in their account. So I thought, well, this is an orchestration problem. So I started using a service called AWS Step Functions, so that I could do all of this in parallel, right? I wanted to test, 128 megabyte, 512, and 1024 megabyte in parallel. I didn't want to wait, because maybe you want to test 10 different configurations and your function takes 20 seconds to run. So if you want to do all of that enough times, it might take you half an hour to do all of it. And I didn't want to wait. So I thought, can I do all of this in parallel? Sure, but then I need an orchestration tool of some sort. So I thought step function, it's a great opportunity to play with it, to learn it, and to build something interesting with it. So cool. I just built it.
That's super cool. So your iteration, and it's still running on step functions.
It is. It evolved a little bit, because back then there was no easy way to build something that would run in parallel based on an input value. So what I want to do is that you provide me the ID of your function, the ARN of your function. You provide me which power configurations you want to test. And based on that, I want to test only those and invoke your functions X times. You can specify how many times as well. And at the end of all of this, the tool is looking at the logs and trying to understand how many times, for how long the function was running, blah, blah, blah. And then it comes back with the result saying, hey, this is the optimal configuration for this function.
That's super helpful.
I think it is. People liked it. And now I think it has something like 1,100 GitHub stars, and we got some contributions from the community as well. So I think I hope it's a useful tool.
I'm pretty sure, at least in my previous life when I was doing this in 2017, 2018, it will save me a lot of nights. Well, maybe not nights, but afternoons of me clicking around and changing values and trying. And as you said, you don't have a statistically significant, you have like an idea what is the best way, and then one thing I was doing is I was leaving it to run in production, and then I was looking at the logs manually and seeing, oh, maybe this is not the optimal, and we could improve it, and it was a lot of work.
Also, because if you do it from the console, every time you change the power configuration, you are likely to hit a cold start. So you have to click test a few times to get the actual execution time. Because, cold starts, as we said before, are not the majority of your execution. So you probably don't want to consider those in your statistics.
Exactly.
And the tool is doing it, by the way. So tool is ignoring automatically all the outliers, like 20%, the best and the worst, so that the outcome is actually statistically useful.
Cool. So the project is alive and it's kicking and it's working and it's contributing. So maybe we can go and see it.
Yeah, I can show it to you.
Because this is not a podcast. We have a screen. So definitely we want to see everything.
Yes.
So please share it.
Let's do it. Let me share my screen real quick. So this is the project on GitHub. And, it's all documented. And if you really want to deploy it super, super quickly, you can actually deploy all of this using the Serverless application repository.
Oh, so it's available there.
It's available as an application in the repo. So in basically one click, let me show it to you. So this is the AWS Lambda Power Tuning app. You can check it on GitHub. A few people already deployed it, a few hundred times, probably more. And here you also have all the documentation. So this is the input JSON payload that you need to use, and all the inputs and the outputs are documented. Anyway, when you're ready, And when you have reviewed the license and the permissions and everything
Everybody
else, you can
reviews
just,
the license all the time.
of course, all the time, you can just click deploy. Let's do it together. So this is more like a demo, I guess.
Sure.
It just became a demo. Great.
We want to see everything, and that's the nice thing of interviewing you with a camera, that you can show us things.
So the best part of SAR, the application repo, is that with one click you can review the template, and once you're ready, you just specify an application name. Let's say Power Tuning, not a podcast, just so we recognize it. Couple more parameters. These are the defaults. They work pretty well. If you want better security, so that the state machine can only work on specific Lambda functions, these are the default power values. And this is the visualization that we haven't really talked about yet, but I'll show it to you in a second. And then you just confirm the deployment.
So you leave even the visualization URL, you just leave it there. Okay, awesome.
Yep, I'll show it to you in a second. Basically, it's a front-end, client-side only static website that will show the results visually. So you don't have to look at the numbers. It's much easier to look at a chart. So what's happening right now is that CloudFormation is deploying all the resources. There are a few IAM role. It's all list privileges. All these roles are optimized for list privilege. There are a few functions, I think 5 or 6. And
it's running in all the functions on your account in that region.
In every region, even across different regions. So you deploy once.
Wow.
Yep. Yeah.
So now
I needed to change a little bit the code to make it work, but now you deploy once and every region works.
Unless you give particular IAM permissions, it will run all the functions in all the regions.
Yeah,
with one
because
click.
of that star.
Wow. That's so
if you want, you can customize that. For security, maybe someone in your organization will tell you, yes, deploy it, but only with this prefix. So it will apply only to some of the functions. Okay, now it's deployed. Let me go to the application. This is a serverless application, right?
Yeah.
So we can see all the resources. Here we go. There are a few functions, 1, 2, 3, 4, 5, and also a state machine. If I open the state machine, well, there's nothing because there are no executions yet. But what you need to do is you need to start a new execution. Okay. And what do you need? You need a JSON input. And well, let's go back to the documentation. Let's copy this in here. Okay, so we need an R of one of the Lambda functions we want to optimize. We need the power values we want to test. We need to specify how many times we want to run each configuration. So let's say, 50. The minimum is 5, but if you only run it 5 times, it's not really that statistically relevant. You can specify a payload if the executions are running in parallel.
It will run 50 times, 128, 50 times, 256, and so on. Okay.
Correct. And all of that happens in parallel if you enable parallel equal true. And I didn't mention it, but you can specify the optimization strategy as well. So it could be cost, it could be speed, or it could be a weighted number so that you decide what's more important for you, speed or cost. So now let's go and take one of the functions I already have. So I have a beautiful function that is computing prime numbers up to 1,000,000, 1,000 times. Super useful, but hey, it's a demo. So this is the ARM. Just wanted to show you this is a CPUbound workload. So we have a clear example of that. Yeah. Now everything is ready. I can give the execution a name, like first execution, but otherwise it's a random string.
Yeah, exactly.
Start.
But this is really nice that the user interface is kind of the step function, so you save so much time on creating a user interface for this.
Well, you can do all of that with the CLI, and I'll show how to do that too. So now the state machine is initializing everything, so it's creating a lot of aliases and versions, so you can run everything in parallel. And now there's this executor function that is executing each branch in parallel for each power configuration. And in a few more seconds, we'll see that there are a couple more functions running: the cleaner, the analyzer, and the optimizer. Each one does one thing. Some of these features are optional, like the final optimizer will actually do something only if the auto optimization option is enabled. So maybe you want to integrate this in your CI/CD and run this at every deployment. So at the end of the execution, it will automatically set the optimal value, for example.
Oh, nice. So it will decide it for you. That's super cool.
Yeah, so you just don't think about it. So it ran. Let's
that was
have
fast.
a look at. Yeah, because I think the slowest execution is about 25 seconds and everything runs in parallel.
Yeah.
So we just did 50 times 5.
Can you hit your Lambda limits with this?
That's possible. So if you say num is 1000 and you test 25 power configurations, yeah, you will likely hit your limit. So do some math there.
Yeah, exactly. That's important for people to know.
Absolutely. I did that a couple of times. I think now it's easy to get up to 3000 without any manual approval.
Oh, so that's the new limit.
So, okay. Yeah.
Because they keep on changing it, because it was 1000, but I don't know.
Yeah, it should be easy. So what happened is that, so I tested these power values, 128, 256, half a gig, 1 gig, 2 gig, and 3 gig. And the outcome is that, hey, the optimal value is 1 gig.
Nice.
Could you imagine that? Well, I talked to a lot of developers that automatically set the optimal value to 1 gigabyte, and sometimes that is true. But hey, I'm not testing 1.5 gig, so that might be optimal. So I'm just not testing it right now. I can tell you it is better. But hey, so I also get the average cost per execution and the average duration per execution. So this is 3.5 seconds.
Oh, so it's quite a long execution.
It's quite a long because it's very CPU intensive.
Exactly.
And the best thing I think that comes with the tool is this visualization. So until 6 months ago, it wasn't there. So if you have used the power tuning app like a year ago, maybe check this out. You get this website, lambdapowertuning.show, and this encoded data, as you see using the hash. So this data is not actually sent to the visualization server. It's only used in the browser. So there is no, data sharing there is no data. So let me show you what this is. So it's clearer. When you open this, you get an actual visualization of the tool. Cool. Let me make it bigger. So these, on the x-axis, you have all the different power options that you tested. If you tested more, you would have more options. And then you have two curves. One is for time, the red one, and one is for cost, the blue one. Now, this is one of my best patterns because execution time is going down, right? As you can see, the more power you give it, we go from 32 seconds down to only 2 seconds. So that's a pretty
big
significant improvement. And the most mind-blowing part, in my opinion, is that the cost is not going up. The cost is going down. So if we use 1 gigabyte, so the cost per execution goes down about almost nothing, but it goes down. So at scale,
that's what you said at the beginning, that cost and speed can be hand in hand in this.
Yes.
In
so
serverless.
This is the part I'm really excited about. Imagine this is a latency sensitive workload. Okay, maybe you wouldn't have an API that responds in 32 seconds, but imagine that was 3 seconds. Okay, you can make it faster, maybe 10 times faster, like in this case, from 32 down to 3.5 seconds, 10 times faster, and also cheaper. Or in the worst case, it might cost the same, which is still incredible as a result, in my opinion.
This is really cool to see. So.
Yeah. And so, I mean, you don't have to use this visualization, and you might even customize the visualization URL if you want to build your own, but this is also open sourced. So if you check it on GitHub down here, you can check the project, and this was a community contribution. I didn't build this. So I think this is the best part. You can build a project. I built it almost 3 years ago, I was still a customer, and now other customers are helping me improve it. So I think that's great.
Yeah, that's super cool. But I think the visualizations are great tools to also negotiate things at work. If you have to go to some architectural meeting and you have different stakeholders and you show data, it's so much easier to get things approved and to have like a validation on why you make some decisions. So I think these are great tools. You just copy paste it and put it in some document and you say, hey, I make this architectural decision because of this, and nobody can come and complain about that.
Absolutely. And even the idea of visualizing it, it makes it so much easier to understand what's the optimal trade-off. Because sometimes, yes, maybe it will be 10% more expensive, but it will be 3 times faster. Is it worth it? Is it not worth it? Just understanding these patterns, looking at numbers is a nightmare, and most humans can't do it. I can't do it. So it's much, much, much easier to look at a chart and understand. So I wanted to remember that these 2 curves are completely independent, meaning they are plotted on 2 different axes. So the fact that they meet here doesn't mean anything. Exactly. So a lot of people told me, hey, should I always choose the point where the 2 lines meet? Nope, that's not the idea. You should look at the numbers, maybe find the best balance between the lowest cost and the lowest execution time.
Because even if you see in the 2 gigabytes, it costs the same that it cost for the 128.
Let me show you something more.
So that's really interesting.
You can start a new execution right from here. And instead of giving a list of values, you can do this magic.
All.
So if you say all, do you know how many memory configurations there are?
No idea.
Available. I think there are like 46 different. So it's very unlikely you want to type them all, and it's a very big number and it takes some time. But if you just say all, the state machine will test all the possible power configurations.
And that's how you hit your Lambda limits of limits.
Yeah, exactly. I think now I have num equal 50, so I'm probably going to hit it. Let's see what happens. 50 times, I can't do math while I'm recording.
Don't worry, we will not chat you.
But hey, I think it's an even easier way to test, maybe 20 instead of 46 possible values. Usually I test the main ones, but what I actually recommend is that when you find let's say a local optimal value, you can maybe be more granular around that optimal value and add more values around it so that you can find the global optimal value.
Yeah, because now, for example, you have find 1 giga and you can try maybe from, 800 to 1 giga and a half, or from, until 2 gigas, and see if there is something in the middle that is best. But that's something that maybe not all.
I've run this already in the past, and I know that the optimal value is about 1.8 gigabytes. So it will keep being faster and cheaper until then, and after that, it will start to be a bit more expensive, but only because the algorithm I'm using is not using the 2 cores that are available. So if the code you're running can actually do multi-threading, it's likely that even after 1.5 gigabytes, it will keep being cheaper and cheaper. So while this runs, maybe I can show you some other things. Well, we'll go back to this. I actually wanted to show you, I prepared some slides here. I wanted to show you another way to look at the problem. So this is what I call CostAware Performance Optimization. Let's play a game. Let's imagine we have 2 functions, A and B, right? And this is what we know. Function A runs on average 310 milliseconds. So what do we pay for?
Yes,
400 on average.
Yes.
And function B runs for 480, which means about 500 on average. That's what we pay for. Now, let's imagine that we run a very quick analysis and that we learn that we can optimize function A about 5% if we do some memory tuning or code improvements, and function B 15%. So I know a lot of developers that would just go straight into B because, maybe this is a latency sensitive customer facing application. So you can shrink and cut off more milliseconds. So that's a better user experience. But if what you're trying to do is optimizing for cost, the reality is that, let me show you the numbers.
Exactly.
With function A, we are going down one level. So from 310 to 294. So we now pay for 300 on average. So we are paying on average 25% less. While for function B, yes, we have cut 72 milliseconds, which is much more. But, if you look at the cost, we have it optimized 0.
Yeah.
So this is a different way to think about this.
And that was what I was trying to do when I was a customer as well, trying to find the sweet spot of trying to utilize those 100 milliseconds that I have as much as I could, because most of our operations were not performance in the sense of sensitive. So we were always trying to optimize for cost. So most of my tuning was manually trying to fill as many milliseconds as I could until the border of just taking advantage of that. So I really feel this pain, and it's so nice that now there is a tool so people don't need to spend hours just clicking.
Well, or at least the tool might help you understand which functions are easier or more worth optimizing. So that's still an improvement in my opinion.
Definitely.
And this is Lambda Power Tuning. That's the project. That's the URL. Maybe you will share it.
I will put it in the description box, all the links that we talked today, so there people can find them and play with it, because I think it's quite interesting.
I've showed you the input already. I showed you the output already. What I wanted to show you are some actual examples, because I've only showed you the prime numbers. So maybe you are curious to learn about some other examples. Let's go for it.
Go.
So there are different patterns, and this is another game I'm running lately where developers show me their pattern, their chart, and I try to guess what their function is doing, because the more I look at these charts, the clearer it is the relationship between what the function is doing and what cost performance pattern will result. So if it's a CPU bound, network bound, or if it's calling a third-party API, meaning out of AWS or not. So let me show you some of these patterns. The first one is what I call NoOp, meaning that it's not doing much, it's not invoking an API, it's not using the SDK, it's just computing business logic, maybe returning a JSON or filtering some input data. But what is critically important is that these functions run for less than 100 milliseconds.
That's a very typical use case, I think.
Very, very common. And whatever you do, there is no way to make it cheaper. In fact, if you look at the blue line, it always goes up. Whatever power you give it, if you use 128 megabytes power, it's always going to be the cheapest.
Exactly.
What I did not expect, though, by looking at this chart, is that sometimes giving it slightly more power, so a bit more of memory, can increase the performance. So if these functions are, I don't know, an Alexa skill integration or an API, or maybe part of a microservices architecture where every single millisecond counts because they will all add up at the end. So in this example, if I give it twice as much memory, so 256 megabytes, I go from 5 milliseconds to 1. Okay, are those 4 milliseconds worth paying something like, I don't know, 10% more in your use case? Up to you.
Exactly.
But I think this is interesting that you can find the optimal trade-off.
And then the kind of performance is very flat. So
yeah, exactly. After that, But what I didn't expect is why using 128 if I can get faster and basically pay the same.
Exactly.
So sometimes it's not 5 milliseconds. Sometimes you're running for 25. And maybe you can go down to 6 or 7 milliseconds. So it might be worth it.
And for some functions that are customer facing, I think it's critical to have faster functions, because the more you make the customer wait, the more chances that they leave, at least in the first interactions, that they are not already committed with you. So these type of things, it's very eye-opener to see. Like,
absolutely.
Just by improving.
Could be an API, could be a RESTful API, or could be a lot of other things that there is a human waiting for it. Yeah. Imagine I mentioned Alexa, because if you are running a Lambda function for Alexa, there is a human waiting for your response at the other side. So you want to be as quick as possible.
Or then for functions like, I don't know, API gateway authorizations that you might be running a lot in between all your API gateway calls. And you don't want to add 100 millisecond lag in between.
Absolutely. So this is a
really
special type of functions because, well, you can't make them cheaper, but you can make them faster sometimes. So I think they are still worth optimizing sometimes, or at least run the power tuning tool and see, what data you get back. What I learned from this story is that you want to be as much data driven as possible. Running this state machine is basically free. It's like in the order of, I don't know, 0.001 cent of a dollar per execution. So just don't even think about it. Second category, we already saw an example of CPU-bound workloads. Yeah. So this is another one, slightly different because it's doing very intensive scientific computation. So it's using a library called NumPy to generate and then manipulate a matrix. Now, as you can see, the execution time is going down very quickly. So this is good. It's from 9 seconds, 9.5 seconds, down to less than half a second.
Exactly.
So that's a good improvement. If this was a latency-sensitive customer-facing API, just give it 3 gig. Don't even think about it. Especially because the cost doesn't change that much.
It doesn't.
So I think the ratio between 3,000 and 128 is something like 1/30. So it should cost 30 times more. But it doesn't.
No.
It costs you something like 20% more.
Exactly.
Because you can be much faster. So that's the beauty of function as a service, in my opinion.
It's pretty crazy to see, because sometimes you think that the cost and the performance are so related and they grow linearly. Well, invert, how you say it in English, when they are inverted in the linear, like more
inversely proportional.
Yeah, inversional proportional. So when you see this graph, it's kind of destroy that idea that you have in your head on how they behave.
Exactly. So you can't make it cheaper, but hey, I think being about 15 times faster is worth spending 20% more. It depends.
It depends on your use case, but I think it's pretty interesting to see and have this material to be able to make the reasoning about.
And this is the example we already saw together like 10 minutes ago. This is my favorite type of pattern because with more power comes also cheaper cost, not only a lot faster execution. So I think this is the best case you can be. If you know that your functions are CPU intensive, it's likely that they fall into one of these two patterns, the previous one or this one. If you're in this one, it's great. You can make it cheaper and faster. You are, in the best situation possible. What I suggested, as we already talked about, is, hey, it looks like 1.5 gigabytes is optimal here.
Exactly.
But can we do even better? So this is what I did. This is what I wanted to show you. So here I tested all the possible values. You don't have to do it. You can just look for maybe an interval around the optimal value and check another 5 or 6. But what happens here is that up to about 1.8 gigabytes, it's still cheaper and still faster. So don't stop at 1.5 gig. You can make it even better.
I didn't know that there were so many values. I just play with the main ones. The ones that you show at the beginnings those are my kind of.
I know. And well, you probably don't want to test, I don't know, 384 megabytes. Why?
Oh, why?
But hey, it's fun. It's even nice to plot in a chart.
Yeah. And if it does automatically, it's not your problem. It's just a
right. It's not my problem anymore. I can just click a button.
Exactly.
So let's change completely the type of workload. So here I'm talking about a network-bound workload, and I call it
example of a Lambda function.
Yes, I call it third-party API. Third-party meaning out of AWS.
Exactly.
Okay. This is very typical too. Maybe you are integrating with a logging service or an authentication service or whatever other, cat facts API, whatever.
That
Jokes, absolutely. So what happens, and this is very easy to imagine if you think about it, is that whatever power you use, you're not going to change the speed of this third-party API. They will have the same. Maybe there will be some slight differences if the payload is very heavy, because the network bandwidth will be better if we have more power. Oh. But in general, it will be hard to make it cheaper. So similarly, as you can see here, the blue line is always going up. So the cheapest option is always 128. So if you're doing this and there is no one waiting for a response, just give it 128. There is nothing you can do to make it cheaper.
The execution time is very flat.
Execution time is flat. This is kind of the worst case scenario where, well, whatever you do, you can't really change the performance of that third-party API, right? No. So just if there is no one waiting for this response, just give it 28 megabytes. You can really do much better than that.
And if someone is waiting, make it asynchronous so they don't need to wait for this.
Exactly. So in this case, you want to optimize the experience by changing the architecture, not by optimizing the individual functions. Exactly. This is slightly different if you are transmitting a lot of data, but we'll look into that in a second. So let's imagine that the API calls you are doing are within AWS. Okay, this is slightly different because of the internal networking. That's how Lambda works. That's how the data centers and the availability zones work. So in this case, I am doing 3 DynamoDB queries in a row, in series, right? There are cases where you need to read and then write something in another table, do stuff, right? And it's likely that these functions will run for more than 100 milliseconds. So if you can increase the network, you can actually go below the 300 and maybe even below the 200 milliseconds interval. And that's what's happening here. So if I give it 128, I'm running for 340 milliseconds. And now I give it more power, I'm running 160. So I went down one level. And now I give it more power and I go down one more level. I'm at about 45, 50 milliseconds. So this is the optimal value.
Exactly.
I can't go much more, I can't make it cheaper at this point. And the performance is not getting better either. So this is the optimal trade-off. Can you see it?
Yeah, but it's very interesting to see these things in a graph. I'm super blown away because you never think about it's an internal call, so maybe then you're blah, 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 your network is more important. You just think, it's a call to somewhere, then nobody cares. But
exactly.
No, this is very important.
Yeah, and well, if you're doing only one DynamoDB query, this is less likely to happen because it's probably less than 100 milliseconds already. But for all those
Dynamo is very efficient for reading, but for writing, it's not as efficient than reading. And if you need to do updates or queries or look into indexes, then things start piling up. So it's
correct. Let's look into another example. I have this weird use cases. You should probably never do it. But a lot of developers often need to download stuff from S3. Usually it's, a few kilobytes, but sometimes it might be, a lot more. So I just wanted to give you an example of how this pattern look like if you're downloading 150 megabytes from S3. And you might think, why on earth do you want to do that?
I will not ask.
I have an example for that.
Okay.
Actually, so this is one of the first thing I did because I was doing the machine learning Python.
Yeah.
So I could not load the machine learning model with my deployment package. So what I needed to do was download this big model from S3, where we would just upload the model on S3 and the function didn't even need to be redeployed. Exactly. So not a typical use case, but there are cases where maybe 50 or 30 megabytes you need to download it. Now, as you can imagine, there is not an easy way to make it cheaper. As you can see from the blue line, it's always going up.
Yeah.
The performance changes slightly, but what I learned is that, hey, here I'm using only one thread. So I'm not actually using all the compute and network capacity that my Lambda function has. So you can completely change this. As you can see, we are running in about 6.5 seconds.
Yeah.
And it's costing, kind of a lot. So if we enable multithreading, and this is one line of code you need to change. It's like an SDK configuration, like enable multithread equal 10, for example. This is what happens.
Wow.
So now we are running. So the slowest option is still fastest than before. And the more threads we have, as you can see, after 1.5 gigabytes, we go down about 1.2 seconds. So we're like 6 times faster than before, and actually cheapest. This is still cheapest than the cheapest option we had before. So we can be 6 times faster and 3 or 4 times cheaper just by enabling multi-threading. So if this is your kind of workload, be careful with these charts and diagrams, because maybe you need to change one line of code and everything else changes.
I don't know how many people are aware of enabling this multi-threading and working with the different threads in Lambda functions, because in general people think, oh, there is no infrastructure to manage. So it's like that kind of things you used to think when you were building applications in a server, but it's still relevant. It's something still you need to think about. And
yeah, there are many things, especially in data science, maybe not a lot in web development, where you may consider switching to a multi-threading algorithm instead of your mono-thread algorithm. So with this, you can verify what's the difference. And if you overimpose the two charts, they are very different. Cost and speed are completely different. So just remember it. I don't have any more examples, but I want to go back to this slide. If you get used, in my opinion, if you get used to these patterns, you can very easily recognize what is the function doing. Is it likely to be CPU bound, network bound? Is this probably a third-party API or an AWS API? And maybe we can play a game. Maybe you can send me some charts and I can try to guess.
Yeah, you can do that. I will leave Alex's Twitter in the description box. Just send him random charts and he will try to guess what kind of application you're running. Yeah. So one thing I have from our discussion is that you mentioned that you can integrate this into your CI/CD pipeline to do it automatically. Whenever you're deploying some new piece of code, then the CI/CD will find the right sweet spot for your application. Can you explain a little bit on how that can be done? I think curious.
There are two main ways you could do that. One is, that's the simplest, but also I wouldn't highly recommend it. The one is enable the auto-optimizing option. If you do that, after you run the state machine, it will also update the latest memory configuration of your function to be the optimal one.
Yeah.
Now, that's if you're using the latest version of your functions in production, that might be considered a CI/CD. I wouldn't necessarily do that. You shouldn't be using latest, and probably you want to also update your CloudFormation or your SAM templates or your serverless frameworks templates with the new updated value, but that's an option. So maybe while you are prototyping or while you are experimenting, that's an option. The second option is maybe you have a development, a dev and a staging and a production environment, right? That have an independent pipeline. So what you can do is that in development, do whatever you want. In staging, you can run the power tuning state machine to find the optimal value, and then you take the JSON output, extract the value, and put it in your CloudFormation for the next stage, which is likely production. Yeah. And then you can automate that process.
Nice. And I think that can be very helpful, because then you don't need to really execute this machine automatically. Well, it will execute whenever maybe you can do it through an API or a script or something like that, and then the input can go to the next step, maybe in your CI/CD using code build or some of these tools that allows you to run shell scripting or something like that.
Yeah. For example, actually, let me show you that you don't have to run all of this using the UI, using the web console. Okay, so if we go back to the GitHub repo, you will find a scripts folder.
Okay.
And in this folder, you can see a couple of scripts and also a nice template, for example, to deploy the SAR application, not from the console, but from your CloudFormation templates.
Oh, nice.
But also, you find an execute script. So in this script, you find all the API calls needed to extract the state machine from CloudFormation, to execute, to start the execution, and also to do the polling, to wait for the execution to complete and to get the results back. So you can either use this or customize it for your own CI/CD.
Nice, that's super cool. So then people don't need to write this by themselves; they can just copy paste it.
Yeah, or get inspiration. I'm not a great shell coder, but I think this is a good start.
Yeah, exactly. And it's always easier to have somewhere where you can tune it after than to have to start from zero.
And if you guys want to help me improve it, there are already a few open issues. I think more or less I contribute to this project maybe a couple hours every week. So I try to add comments on issues or pull requests. We had like more than 30 pull requests already merged. So feel free to improve it. For example, the shell scripts are a good starting point if you want to help me improve it.
If there is some shell experts watching this.
Yes, then help me. But also we had some crazy ideas out there. Like some people asked me, hey, can we leverage X-ray to gather even more data about distributed tracing? Or can we use this tool for stress testing? Like I give you only one function and one power configuration, and you just stress test my function. So how does the visualization change? How is it useful to you? Maybe let us know.
Yeah, that's super cool. Yeah, for stress testing, I've been using artillery, and this is way
Definitely
easier
better.
Because, well, I don't know. I like the idea of having it inside the step function, running parallel, and you don't need
I think the most useful part is the visualization. Like you want to do stress testing across multiple power configurations. But hey, I'm still collecting ideas and feature requests, so feel free to join the conversation.
That's good. Yeah. There's something else you want to show us, or?
Let me think. Oh, I actually have a demo. We can share this URL later. So all the demo I've shown you, all the CloudFormation templates, and even the code of the functions we have talked about. So we have the no operations, NoOp function. We have the prime numbers function, which is actually using a layer. So you can learn about layers too.
Yes.
We have the linear algebra one. We have the S3 download. So you can check exactly what code was running and maybe deploy this stack and check the power tuning results yourself.
That's really good. So then people can try it out with real examples and not just the typical hello world Lambda that is the less than 100 milliseconds that you cannot improve.
Correct.
Yes, that's cool. So thank you, Alex, for everything. I have one last question for you. It's like how people can get started with power tuning their Lambdas. How, I don't know, besides the Git repo, is there some other material that you can share with them?
So I'm actually planning to write a nice article about all of this. For now, I think, yes, the GitHub repo is the best way to get started. From there, you find the link to the SAR, Serverless Application Repo. application. You find some links to social media, to the other contributors. So I think that's the best way to get started.
So I will leave that GitHub in the description box. And also, what is your favorite social media where people should contact you? What is?
You can find me on Twitter, but also LinkedIn works, if you're more comfortable with that.
So I will leave those 2 links also in the description box so people can send you questions and ask you whatever they need to know about power tuning.
Send me your pictures and your power tuning results.
Yes, exactly. Just send that to Alex and he will try to guess what kind of application you're running. So thank you very much, Alex, for your time. I hope you enjoyed to be interviewed by me and ask all these questions. But it was great to have you here. Thank you very much.
Thank you, Marcia. Thank you for hosting me.
Thank you so much for watching. I hope you enjoyed this presentation. All the links that we mentioned during this interview are in the description box below. Leave me a thumbs up if you like this type of content, and if you want me to talk about some particular topic or talk with some particular person, let me know in the comment box below. I would love to interview people that you are interested in. Remember, Alex is available through his social media. You can reach him and ask him questions and share with him your screenshots. And next week we have on Wednesday Chef Bar coming to this podcast. No, this is not a podcast. To this YouTube channel to have a chat on how he does to keep up with the cloud. So that's all for today. I hope you enjoyed this video and see you next week with another episode of FooBar. Ciao, ciao!